has negative feedback, right? Because the feedback goes into the inverting pin and the signal gets turned upside down. So if you're kind of sitting on the loop, it's a negative loop. So let's just label which one has more feedback. All right, so it's the one on the left, this one. All right, now let's see what kind of feedback it is. So again, I'll imagine that I'm an insect crawling on the line, and we march towards the amplifier, and then here we crossed the feedback path, so that type of feedback is shunt, right? How about at the output side? Again, I can start at the load and start walking towards the amplifier, and I found the feedback path, so this is also shunt feedback, right? And of course the gain here is a lot higher, right? Because it doesn't have any negative feedback. As soon as you put negative feedback in the circuit, it lowers down the gain, right? And there's a chart in the notes that will tell you what happens to the input and output impedance. Shunt feedback always makes the impedance lower. So that's actually good news at the output side, and it's normally bad news at the input side, right? Because you like the input impedance to be high. We can compare the input impedance before and after. You see this is 0 volts because it's ground, and I happen to know that the gain here is equal to minus RF over 1. It's just a standard configuration inverting op-amp. The gain here equals, let's see, it says in part B, assume that the feedback resistor is 100, so that's minus 100K over 1K. So the gain is minus 100. The gain over here is minus infinity. If this is at 0 volts right here, and you know the gain is a finite number, it means that this has to be 0 volts there, and then it's quite clear that the input impedance is 0. The input impedance here is infinity if it's looking into the pin of an ideal op-amp. So you see, by adding the negative feedback, the gain has dropped all the way from infinity down to 100, and the input impedance has dropped from infinity down to 0. The output impedance, in this case, if it's an ideal amplifier, it would be 0, and it would drop even more in this case. So 0 becomes 0, right? But assuming that the amplifier is non-ideal, then the output impedance will be higher in this circuit than in this circuit because of the shunt feedback. The output impedance will get lower. If the op-amp is non-ideal, of course, the situation with the feedback, with the shunt feedback is going to have the lower input impedance as well. Let's look at the second circuit. And we'll do the same thing. So we'll compare the situation if the feedback resistor equals infinity. So this is 1 kilo ohm. All right, if the feedback impedance is infinite, then it goes around like that. Which one of these circuits do you think has more feedback? The circuit on the left or the circuit on the right? Which one has more feedback? It's the one on the right. But don't feel bad. Whenever I ask the question, almost all the time people will answer the one on the right. I've got to explain it. That's exactly why I've chosen this particular problem to ask. The reason why this one has more feedback is because we can think of it this way. All of the current that passes through the load resistor gets fed back into the amplifier, whereas in the circuit on the left, you see only a fraction of the current that passes through the load resistor gets fed back into the amplifier. See, here it's 100% of the current got back. Here it's only some fraction of it that got back. So therefore this one on the right has more feedback. Now the thing about series feedback is that you should pay attention to the current when deciding how much feedback there is. And if you've got shunt feedback, you should pay attention to the voltage when you're thinking about how much feedback there is. With shunt feedback, you see, you're not sampling how much current there is through the load resistor. You're sampling the voltage at the output pin. With series feedback, you're not sampling the voltage, you're sampling the current that's gone down through the load resistor. And in fact, that's exactly what makes series feedback different from shunt feedback, and that's also why they have opposite effects on the input and output impedances, because one is related to the current and one is related to the voltage. Well, let's calculate the gain in each of these circuits, and then let's also calculate the input impedance to see which one has more. Of course, because I've said this one has more negative feedback, we expect the gain in this case to be less. The gain, in fact, if the op-amp is ideal, is very easy to calculate here. The gain is in fact 0, because if the op-amp is ideal, then this current going through the load resistor has to be 0, right? Because current can't enter there can't be any current that flows into that pin if the op-amp is ideal, right? Input impedance should be infinite. Without any current going through the load resistor, by Ohm's law, V equals IR. If I is 0, then the output voltage is 0. Doesn't matter what the input voltage is, right? If the output voltage is always 0, then the gain is 0. Let's find the gain for the circuit on the left. Now in this case, we've got the signal voltage on this side of the resistor, and again, let's assume that the op-amp is ideal. If it's ideal, then there isn't any current that passes through that 1 kilo ohm resistor because it's ideal op-amp. So without any current, there isn't any voltage drop, so the voltage here is also Vs. If the output voltage is a finite number, that is, if it's not plus or minus infinity, then I can assume that this is also Vs. That's an assumption that we should test here in a minute. If I reach some kind of a contradiction, we'll know that that's the first assumption that might be wrong. Well, if this is Vs, then let me label this current as I. You see, all of that current actually has to pass through RF if it's an ideal op-amp, because you can't have any of it going into that pin, right? This inverting pin. So that means the current here should equal the current here. The current here, V out over RL, should equal the current here, which is Vs over RF. And from that I can very easily calculate the gain. The gain, which is just the output divided by the input, is RL over RF. And now you can see that in fact I was right. This circuit has more gain than this circuit. Therefore we know that this is the one that had more feedback, right? Because we've sacrificed the gain when we added more feedback to the circuit. So the gain here is 0, gain here is RL over RF. Now let's think about the input impedance. So the input impedance, if they're ideal op amps, they're both infinity. So it's hard to compare one infinity to another. So that's why I asked part C up here. If the op amps are non-ideal, how will the input impedance change? Of course, the one with more series feedback will have a higher input impedance than the one with less series feedback. So I can say that the input impedance here is higher. The output impedance, by the way, is also higher in this case because they both have series feedback. And I don't need to actually calculate what it is. You know, I would need to know a lot of information about the op amps in order to know exactly what either the input or output impedances are. But what I can say for certain is based on the fact that it's series feedback at both the input and the output, that both the input and output impedance have gone up when we added feedback. See, we sacrificed some of the gain and we got an increase in the input and output impedance. A lot of time that's not desirable. You know, the best kind of amplifier, at least if you're working with voltages, is the amplifier that improves the input impedance by making it higher and improves the output impedance by making it lower. So the series shunt feedback configuration is usually the most desirable. And you can identify it by inspection, right, from the circuit. It doesn't matter what the amplifier looks like, what the configuration is, whether it's a transistor, an op amp, or a vacuum tube, or a MOSFET. If you can just identify, you know, you imagine you're the ant crawling on the leg, you say series shunt or shunt series, you'll be able to tell whether the input impedance is better or worse. All right, so let's turn it over. Let's look at some of these circuits on the back and get some practice identifying whether it's shunt series. So in this case, I can identify the feedback loop is here. It's got a minus sign in the loop. Therefore, I know that the loop gain, A beta, has to be negative. So A times beta is negative. Gain the loop. Here's the feedback loop for this circuit, and you see this feedback loop doesn't have any minus sign in it. No inversion, nothing that could add a 180-degree phase shift to the signal, so A beta is positive. This one has negative feedback. Let's pause for just a moment and notice that, you know, you might think, oh gosh, you know, what do I do? There's two loops in this circuit. How come I didn't put this one over here? You see, that loop does not contain the amplifier. Right? It goes between two input leads to the amplifier. It's not a proper loop. I can tell it's not a proper loop because I could redraw the circuit. You see this resistor here? That just goes to ground. It's not really attached over there. I could just draw it like that over on this part of the circuit, and it would be the same circuit. And then that somehow makes it clear that it's not a loop, right? Let's look at this transistor amplifier. Now, when you're looking at transistor amplifiers and you're that ant crawling on the line, you have to walk all the way to the transistor. It doesn't matter what kind of transistor it is. If it's a vacuum tube, you walk all the way to the terminal of the tube. If it's a MOSFET, you walk all the way to the MOSFET. Right? You have to walk past all the resistors and whatnot. So there's the collector. So we start here, going down. There's a loop. Now, if I'm a signal running around in that loop, in my path, I have found a common emitter amplifier, right? Because if I'm in this loop, I enter the base and I come out the collector, therefore it's common emitter. That's inverting. That's an inverting amplifier. Therefore, my loop gain is negative. So here we are at the emitter, and I can see a loop here. Now, if I were in this loop over here, I enter into the base and I come out the emitter. That's common collector for the loop. Common collector is a non-inverting amplifier. Therefore, my loop gain is positive. That's an example of, in other words, this is an example of positive feedback that's unstable and probably useless because it's not a filter, it's not an oscillator. It's just an example of a very poor circuit design that doesn't accomplish anything, right? Moreover, in the negative feedback loop, normally when you use negative feedback, there's not really ever a need to do signal filtration in the negative loop. The capacitor here, of course, you need that capacitor to be very large so that it won't add some undesirable phase shift to the signal that runs around in that loop. If the capacitor is too small, then it's not negative feedback anymore, is it? It would be something, it wouldn't be positive, it wouldn't be negative, right? It would have some phase shift that's not zero and some phase shift that's not 180 degrees, right? You can only cause the loop gain to be positive or negative if it's a real number, right? If it's a complex number, which some capacitor inductor can give you, then it doesn't make sense to talk about negative or positive feedback. Of course, if it's positive feedback and you have an oscillator set up, then right at the resonant frequency, the gain around the loop is a real number, and it's 1. For all the other frequencies, that loop gain will be a complex number. It just happens to work out that way. Now let's go back up here and let's find out in each one of these circuits what the sign is for A and the sign is for beta. We can split it up here. So A is the gain of just the amplifier. So let me kind of draw the diagram up here of what I mean. So we've got our signal, and then we've got some amplification, and then we've got our output, right? And as soon as we add feedback, then we've got another loop. So we add the feedback to the loop, and of course, if it's an oscillator, you don't have the input. You just have the loop, right? And the gain around the loop has to be 1 at the resonant frequency. When you use negative feedback, it's usually set up with an input and output. So then it matters to talk about the A and the beta. If you just have a loop, you can't really tell where A starts and beta ends, right? It only makes sense to talk about them together. But as soon as you have an input, then you can tell which one is A and which one is beta. So A is the gain of the signal without the loop. So let's look at these circuits and just imagine that the feedback loop is broken. Would the amplifier be inverting or not? So if I break the feedback path here and just kind of look at the amplifier, it's clearly a non-inverting amplifier, right? Because the signal enters the positive pin, right? So A is positive. Therefore, I can easily tell by comparison that beta is the negative one. let's look at the second one. In this case, the signal enters quite clearly the positive pin, therefore A is positive. And by comparison, I can see that beta is also positive. Circuit C, again, it's very clear that the signal enters the positive pin, therefore A is positive. By comparison, beta is negative. Down here, the signal over here enters the base, and the output resistor is at the collector. So forget about the loop for a moment. It's a common emitter amplifier, right? If the loop is broken. So it's a common emitter for the signal. That's inverting. Therefore, A is minus, and by comparison, beta is positive. Let's look at this one on E. The input is at the base of the transistor. The output is up here at the collector. Notice that in this case it's different if you're in the loop versus if you're the signal when the loop is broken. So if I imagine that the loop is not there, this is just a standard common emitter amplifier for the signal. Common emitter is inverting. Therefore, A is negative, and by comparison, beta is also negative. All right, now finally, let's decide whether these are shunt or series configurations, right? And we'll be done with the problem. So this first one, obviously, we walk over here. Series shunt, right? Because here at the load, we found feedback. Second one, shunt. So then we could have some idea of whether that makes the input and output impedance better or worse, right? This one is series. This one is shunt. This one is shunt series. See, it's a little bit confusing over here. If I draw a line up here, it's still the same circuit, right? So you have to be careful with, the human brain is sometimes not good at this sort of pattern matching. Sometimes you have to imagine little wires. Questions on the circuits here? Maybe I can point out one more tidbit of information. I just love this. If you look at that sheet in the notes at what happens to the input and output impedance in the presence of feedback. For example, series feedback will cause you get a new input impedance and an old input impedance that's multiplied times this number right here. See, if you've got, this is with the series configuration. So series configuration at the input will increase the gain. So now let's look at this equation. If we have negative feedback, then A beta is a negative number, right? Which means that 1 minus A beta, see, if A beta is negative, then 1 minus A beta is a number that's larger than 1. That's why if you have negative feedback, then Rn increases when you add the feedback path, right? But let's just think about the case where you have positive feedback. Of course, if you have too much positive feedback, the thing will turn into an oscillator, right? Then it doesn't so much make sense anymore. But if you have positive feedback and A beta is greater than 0, however, it's less than 1. Of course, if it's 1, you'll get an oscillator. But if you're here, what's going to happen? Well, then 1 minus A beta is now less than 1, and it'll have the opposite effect. Rn will decrease. All right? So that has, I hope you can see from the equation what I'm getting at here. When I talk about whether it goes up or down, I kind of assume we're dealing with negative feedback. If it's positive feedback or regenerative feedback, it will have the opposite. It will have the opposite influence on the input and output impedance. All right. It's been a pleasure having you all in class. I hope you learned something. Yeah, I hope you enjoyed it. I've written what I consider to be very reasonable final exam. No tricks or anything. So I think if you spend time and you practice the old exams and work a lot of practice problems, then you should be very well prepared for the exam, right? So I don't change the questions significantly from the previous, no tricks or anything like that. At least I didn't think there were any tricks, right? But if any of you have questions or anything